Hello everyone, thank you for joining me in my channel on the presentation for the GTAP conference. My research topic is do light vehicle emission standards promote environmental goals in Australia? First, I will talk about motivation. Second, I'll show how I did these simulations or policy schemes simulations in the CGE framework, then report the results. In fact, Australia is one of the largest carbon emitters per capita in the world. The carbon emissions per capita in Australia is very close to the emissions from the USA. In some years, it is even greater than the USA's emissions average. In Australia, the transport sector accounts for more than a quarter of the Australians' greenhouse gas emissions. Light vehicles alone accounts for 10% of the total emissions. Most of them are household emissions. Therefore, the Climate Change Authority of Australia proposed mandatory light vehicle emission standards, aiming to reduce the emissions from the transport sector. What is the proposed light vehicle emission standards? It requires the new cars sold in Australia to reduce from 192 grams per kilometer at current level to 105 grams per kilometer in 2025, which is equivalent to the fuel economy standard 8.3 liters per 100 kilometers in current level to 4.5 liters per 100 kilometers. Australia is not the first one to implement this policy. The United States has the legislation on the corporate average fuel economy standards in 1975, the first in the world to implement the car efficiency standards. And the recent Obama government has incorporated the GHG standards to the policy that in the targeted year 2025, the CO2 target is 93 grams per kilometer or equivalent to FE fuel efficiency target 4.0 liters per 100 kilometers. And EU has compared with other countries has the most stringent standards around the world. Australia has lagged behind many countries in this policy scheme. However, this policy has received many comments or critics after its implementation. The light vehicle emission standards is essentially an energy efficiency improvement scheme, which is a tool in the demand-side management in energy consumption. Early as 19th century, the British economist Jevons has written in his famous book, The Coal Question, that it is a confusion of ideas to suppose that the economical use of fuel is equivalent to diminished consumption. The very contrary is the truth. Many economists have observed that the efficiency use of energy may not lead to the desirable outcomes because of the rebound Here are three possibilities of an exogenous technology improvement in fuel use. First is energy savings, that is desired by the engineers when they found a way to use fuel more efficiently. The second is no effective change, where the rebound is the same as the energy savings. The third is the Jevons paradox, where the rebound is so large that it offsets all the technical savings and even more energy is consumed than before. The theoretical foundations of the rebound effect is grounded in the neoclassical economic theory. When we can use fuel more efficiently, the effective price of fuel actually drops. This will induce behavioral change either in the form or by the final demanders. We can decompose the effects of energy efficiency improvement into two effects: the mechanical change and the behavioral change. The behavioral change can be more explained by the output substitution and income effect. Let's set up the cost minimization problem for the form and see how a technical change affects the final use of fuel for a specific sector, say the transport sector. PI is the firms try to minimize its cost with the summation of PI times Xij, where PI is the price for input I, agent price, Xij is the quantity demanded by demand of input I by sector J. The form faces Leontief production function. This actually simplifies the behavioral effect because there's no substitutional effect in this production form. Now we only think about a specific effect and a direct, and we only consider the direct rebounds in the same sector. That is fuel denoted by 17 and the transport denoted by 26. When a technical change happened in the transport sector and only on fuel use, the demand of fuel in the transport sector is the change in transport output plus the technical change or the mechanical effect Aij. Now we only think about what happens in a partial equilibrium model because this simplifies a lot of things. In the partial equilibrium model, we can write demand change Yj as the price change times the elasticity of demand, denoted by eta j. And the effective price change is the cost share of petrol in transport times the mechanical change or engineering advancement. The break-even condition says the change in fuel use in the transport is zero. This implies the equation first one y, the absolute value of yj equals aij. And if we plug the second equation into the first equation and set it to zero, we can solve for eta j. So the elasticity is the inverse of the cost share of petrol in transport. And if the elasticity is greater than this cost share, then the more fuel would be needed for this sector. While the partial equilibrium model implies that the rebound effect is direct and small. And since it has to be greater than the inverse of the cost share, it has to be really large, and usually the elasticity is around 0.5, between 0.5 to 1. This means rebound. Even though there is a rebound, it is not big enough to offset the overall mechanical savings. However, the partial equilibrium neglects the income effect and the interactions between the industries. Therefore, we come to use the general equilibrium to take into account the income effect and the interactions between industries, so we could estimate indirect and economy-wide rebound effect. We also need to note that if the technical change is small, the result from the general equilibrium modeling would not differ much from that found in the partial equilibrium framework. First, let's consider the business as usual scenario, which provides the baseline to compare with the policy simulation. During the business as usual scenario, we have first to predict what happens to the fuel efficiency levels without any policy intervention. The graph shows the evolution of the fuel efficiency from the 1970s to 2015. We can see there is a cyclical change pattern there. So I used the Bayesian econometrics to fit this model and predict what happens in 2025, and the prediction is 7.3 kilometers per liter, which is 1.6% technical improvement compared to the level in 1994. Then I decomposed the business as usual into two scenarios. 1A is the industrial shock, the petrol use in transport, and the second scenario is the household petrol demand taste shift. Experimental environment is RNG, a multi-sectoral model for Australia, which is comparative static with 35 industries and 37 commodities, 3 primary factors, and optimizing behaviors of agents through pure profit and market clearing conditions. The long-run closures were used in all these scenarios, assuming adjustable capital stock and fixed employment. This table shows the results for the simulations and the business as usual scenario. In the first column, where there is the technology improvement in transport fuel use, the GDP increases as expected, so is the household consumption. The intermediate input change of petrol in transport decreased by 1.33, and the desirable result, or the mechanical change we have imposed on, is minus 1.6. The difference between 1.32 and 1.6 gives the direct behavioral effect, which is 0.28. To get the direct rebound effect, we use the direct behavioral effect divided by the desirable mechanical change, which is minus 1.6. So the direct rebound is 17.5%. And now we want to calculate the indirect rebound. We need the output change of petrol. The overall output change in petrol is minus 0.33. The mechanical effect of the overall petrol is the transport, the quantity share of petrol used in transport, which is 45% times the mechanical change. This gives the minus 0.72%. Difference between the output change and the mechanical effect gives the indirect behavioral effect 0.39, and if we divided this by the desirable mechanical effect gives the indirect rebound, which is 54.2%, which is quite large. This implies that 54% of the mechanical reduction has been offset or ruined by the rebound effect. Scenario 1b gives a very different or nearly opposite results. In scenario 1b, we shock the household fuel consumption. We assume that the household can consume less fuel but remain the same utility. This negative shock on consumption has a negative effect on GDP and household consumption. But we have to know that the welfare actually increases. The household petrol consumption decreased by 1.56. This figure is quite close to the mechanical change minus 1.6. Only 0.04 is the difference or the direct rebound, and if we divide it by mechanical effect, gives the direct rebound, which is quite small, and the indirect rebound is small too. How do I simulate the mandatory standard in the model? I simply combine these two shocks, but with a larger magnitude, minus 3. This implies the average fuel efficiency level will reach 7.4 kilometers per liter. The results shows these shocks have a positive effect on GDP, but a negative effect on household consumption. As before, the welfare of the household increased. The output of petrol changes by minus 1.36%, whereas the mechanical effect ME in the third column is 2.34%. This is calculated by 3% times the household share and the industrial share of petrol use, which is 33% plus 45%, around 78%. The difference between the two and divided by ME gives the RE rebound effect is 41.9%. The intermediate input change is minus 2.5, where the target is minus 3%. So calculate the difference is 0.5 and divided by 3 is 16.7% rebound. Lastly, the household petrol consumption decreases by 2.9%, which is very close to the targeted number 3%. The rebound is only 3.3%. So what do we learn from these policy scenarios and business' usual scenarios? We learned that under the business' usual scenario, the fuel efficiency improvement induces more rebounds than in the industrial sector than in the household shock scenario. That's because in the industrial shock, there is a technology improvement which boosts the economic growth, whereas in the household shock, there's a negative household consumption shock that is bad for the economy and especially bad for the fuel or petrol industry. Second, in the policy scenario, I combine the industrial shock and the household shock, which would larger tech change and the larger negative consumption shift, which induces small indirect rebound, but a large indirect rebounds on fuel consumption. Rebound effects Overall, rebound effects are large and could undermine as much as 40% of the technical gains in energy savings in the policy scenario, but this figure is even larger than the business as usual scenario. What I'm also looking forward to doing is include link these results with the carbon emissions account and more vehicle compositional change analysis, maybe econometrics, so I can come up with more accurate scenarios and then use the dynamic modeling considering the economic and population growth. Thank you for listening.